The following program is made possible in part by the U.S. Environmental Protection Agency, Missouri Department of Agriculture, and University of Missouri Extension.
Well, we do see drift being a significant issue in agriculture and in the urban settings in Missouri. Besides, damaging crops, the human exposure one that definitely is something that we look into very closely. Every pesticide applicator, no matter if it's a commercial applicator, non-commercial applicator, or a homeowner, all applicators have to follow and read the pesticide label to give specific directions on how to mix, store, apply, and dispose that pesticide. The label is the law. And as the Department of Agriculture, being a regulatory authority, we do have to take action when we find misuse from the applicator, including pesticide drift.
The spray drift of pesticides away from the intended target is an important and costly problem facing both commercial and private applicators. Pesticide spray drift results in a number of problems, including damage to susceptible off-target sites, lowered rates of application, reducing product effectiveness and resulting in product waste, and the accumulation of illegal pesticide residues that can damage property, the environment, and even public health. In this presentation, we will examine how pesticide spray drift can occur, and perhaps more importantly, the role of both applicators and regulators in preventing spray drift and responding to a spray drift incident. We will see how equipment, weather, and other factors impact the potential for spray drift. The Environmental Protection Agency defines pesticide spray drift as the physical movement of a pesticide through air at the time of application or soon thereafter to any site other than that intended for application, often referred to as off-target.
Environmentally, when you look at how the products will drift, we can end up with high concentrations of the chemical downwind side of the field. So it'll be collecting in the fence rows and buffer zones and trees or in low areas there, which then can get into the water systems, the creeks and the waterways and ponds and rivers and such.
EPA's definition does not include the movement of pesticides to off-target sites caused by erosion, migration, or contaminated soil particles that are wind-blown after application, unless these conditions are specifically addressed on a pesticide product label with respect to drift control requirements.
Pesticide drift is a major concern with the Missouri Department of Agriculture. Drift can occur in agriculture, but as well as, for example, in lawns applications, right-of-way applications, or mosquito applications.
Spray drift occurs when the nozzles of spray equipment produce droplets of pesticide solution small enough to remain suspended in the air. These droplets can then be carried by air currents to areas other than the target site. Drift can be influenced by a number of factors, including weather conditions, topography, the crop or area being sprayed, application equipment and methods, and of course, decisions by the applicator.
Pesticide drift could occur, for example, by traveling too fast through the field, or setting your PSI too high, or having the boom height too high, the wrong type of pesticide nozzle, are just an example of several ways that drift could occur.
Each year, there are thousands of reported complaints of off-target spray drift throughout the United States. These drift incidents are an important component in the scientific evaluation and regulation of pesticide use. When pesticide labels state that off-target drift is prohibited or to be avoided, EPA policy is definitive. Pesticide drift from the target site is to be prevented. Although some degree of spray particle drift is almost inevitable, The EPA expects prudent and responsible applicators to know and understand a product's use restrictions and to use all available application practices to prevent drift. Applicators must consider all factors when making pesticide application decisions: wind speed and direction and other weather conditions, application equipment, the proximity of people in sensitive areas to the application site. The toxicity of the pesticide and the product label directions are all important factors in determining the potential impacts from drift.
Some of the biggest steps that any grower, custom applicator can take to prevent drift is to really understanding the product that they're applying and the environmental conditions that are around them when it's time to apply.
Applicators are responsible for complying with laws regarding pesticide application and must refrain from application under conditions that are inconsistent with the goal of drift prevention or that are prohibited by the label requirements. EPA has discretion to pursue violations based on the circumstances of each drift situation. Under federal law, EPA's Office of Pesticide Programs is responsible for evaluating pesticides and their uses, and to ensure that they can be used with a reasonable certainty of no harm to human health, and not cause unreasonable risk to the environment when properly applied. The OPP considers the potential impact of spray drift on humans and the environment in the evaluation of proposed pesticides for new registration and older existing pesticides for re-registration. Based on these evaluations, OPP may impose specific restrictions for a pesticide's application, which may prohibit the product's use under particular conditions, or prohibit certain methods of application. The OPP may require the use of a foliage barrier or a buffer zone between the application site and areas to be protected. A buffer zone is an area where pesticide is not directly applied, thereby providing protection to a defined area. For example, the application of atrazine requires a buffer zone of at least 66 feet between the application site and any waterway. Complaints regarding off-target spray drift should be reported to the state or tribal government agency which is responsible for enforcing the proper use of pesticides for that particular state or tribe. These agencies have the primary responsibility of enforcing lawful use of pesticide products by investigating complaints and, when appropriate, issuing penalties for improper use. The EPA will assist these state and tribal agencies when necessary.
Missouri Department of Agriculture is responsible for regulating the use of pesticides in Missouri. It is established by Section 281.005 through 115 of the revised Missouri statutes, also known as the Missouri Pesticide Use Act.
Should you believe that you have been exposed to pesticide spray drift and have health-related questions, contact your physician, local poison control center, or health department for assistance. You can also contact the National Pesticides Telecommunications Network. For general information on EPA's pesticide program, call the Office of Pesticide Programs or visit the EPA pesticide website. Spray particle drift occurs by two methods: vapor drift, associated with volatilization, and particle drift, movement of spray particles during or after the spray application. Although serious problems due to vapor drift are somewhat rare, it is possible for concentrations of vapor to move across the landscape until they are deposited in a large enough concentration to damage susceptible non-target plants.
With those molecules that are more likely to volatilize, they can really be deposited on the crop and the weeds fine, and you might not have had drift, but then you get a temperature regime and everything that lines up that would allow that pesticide to escape in a gaseous form, and often it will move over and set down in a lower area. It could be of the same field, or it could be somewhere where it's not supposed to be.
Under normal weather conditions, warmer ground air tends to rise and mix with cooler air in the upper atmosphere. This permits pesticide spray droplets to disperse as intended and usually pose no problem. However, in a temperature inversion, the ground level air is covered by a layer of warmer air. This warmer layer acts as a cap, preventing the normal mixing of the atmosphere. Under these conditions, the small suspended spray droplets may volatilize and form a concentrated cloud and move in unpredictable directions. Recognize the potential for temperature inversions when the sun is low or at night. Also when winds are light or undetectable, especially during early morning hours after a clear night. A smoke trail can be a good indicator of how vapors will behave. Smoke that rises and disperses is a good sign. Smoke that travels slowly near the surface indicates a temperature inversion and conditions that are favorable for vapor drift. Vapor drift can occur with all product formulations, but is generally higher for more volatile spray formulations. That is, esters as opposed to amines. A volatile formulation readily evaporates into small particles, affected more by air movement than by gravity. Hot, dry air increases evaporation rates and quickly reduces droplet size, increasing the risk of drift. Spraying when temperatures are cool and humidity is high, such as during the morning hours, minimizes volatilization. Wet soil also increases the rate of volatilization and decreases the effectiveness of soil incorporation. Both of these effects increase the risk of vapor drift of soil-applied volatile herbicides. Within the next 2 years, it is expected that varieties of corn, soybean, and cotton will be introduced with traits that confer tolerance to the herbicides 2,4-D and dicamba. Although pesticide applicators have utilized these herbicides for many years, the introduction of these new traits could result in a substantial increase in the number of applications of these active ingredients. Consequently, pesticide applicators should be aware of this development and take appropriate steps to avoid the risk of off-target movement of 2,4-D and dicamba to gardens and sensitive crops such as grapes, tomatoes, tobacco, and even to soybeans and cotton that do not exhibit tolerance to these herbicides. Particle drift is the most recognized type of drift, and although it can't be eliminated, particle drift can be reduced to very low levels through proper nozzle selection, equipment operation, and other management choices. Nozzle selection affects practically every aspect of particle drift and offers many choices of droplet size and spectrum. And although nozzles are designed to produce only a narrow range of droplet sizes, in reality they generally produce droplets that are both larger and smaller than what is intended for a particular application. Droplet size is measured in microns. A single micron is 1/millionth of a meter. Consider a human hair is about 100 microns thick and fairly visible due to its length. However, particles or water droplets less than 100 microns in diameter are practically invisible without magnification. The term volume median diameter is used to indicate the relative droplet size of a volume of spray from a nozzle. A VMD of 400 microns means that half the volume of spray will consist of droplets with a diameter of less than 400 microns, and the other half will consist of droplets larger than 400 microns. Because smaller droplets have much less volume than larger droplets, most of the droplets will be smaller than the VMD. These smaller droplets are highly subject to drift. They fall more slowly and so are airborne longer, and thus are carried farther by air movement. Small droplets also tend to evaporate quickly, leaving minute quantities of the pesticide in the air. Ideally, most of the spray volume should be contained in larger droplets, which maintain a downward velocity longer and are more likely to be deposited on the intended target. Drift is more likely the result of turbulent air than of gravity. The initial size of the droplet is the most important factor in drift. The best droplet size for a particular application is a compromise between drift reduction and adequate coverage. Droplet size should be no smaller than what is needed to obtain good coverage. Droplets that are too small typically never reach the target anyway. These are the generally accepted values for various pesticide products. While smaller droplet sizes are required for good coverage of some fungicides and insecticides, the nozzle must be positioned close to the foliage for the spray to reach the target. Droplet trajectories are affected by their initial velocity and momentum, gravity, friction, and the temperature, humidity, direction, and speed of the air. Small droplets lose momentum quickly due to the frictional forces imposed by traveling through air. Droplets less than 20 microns in diameter decelerate within an inch of the nozzle and then depend primarily on air currents to determine their destination. Larger droplets of 200 microns in diameter decelerate within 19 inches of the nozzle. Droplets with a diameter of 200 microns are generally considered the smallest droplets with a reasonable chance to reach the intended target. This 200 micron threshold is determined in part by the practical setup of a spray boom with operating characteristics that provide uniform coverage. For booms with nozzles on a 20 or 30-inch spacing and with fan angles of 90 or 110 degrees, a boom height of 18 to 19 inches above the target is generally recommended for ideal overlap. When measuring from the top of the canopy, it is usually better to be a bit closer than your calculations indicate and minimize the distance a droplet travels to reach some part of the target. Although the operating characteristics of nozzles can vary, most can provide an acceptable range of droplet sizes when operated within their rated pressure range, especially near the low end of that range. Select a nozzle based on its intended use and the rate of flow it is expected to supply. Select a nozzle large enough so that the operating pressure is near the low end of the rated pressure range. EPA registration labels for some herbicides specify nozzle type and sprayer pressure range, as well as which additives may be used, and the maximum wind speeds in which the pesticide can be applied. Flat fan nozzles are the industry standard and provide excellent uniformity when the fan pattern is adjusted for 100% overlap. The characteristic fan pattern is formed as the pressurized spray solution is emitted through an elliptical orifice. This creates a thin spreading sheet of liquid that breaks up into droplets shortly after it leaves the sprayer tip. Increasing the pressure creates smaller, more drift-prone droplets. Standard flat fan nozzles are generally rated between 30 and 60 psi. Operating pressures between 30 and 40 psi are recommended to minimize production of fine droplets and reduce drift. Pressures below 30 psi result in a poorly developed and unpredictable spray pattern unacceptable for uniform coverage. Extended flat fan nozzles, as the name implies, can be operated over a larger range of pressures, typically 15 to 60 psi. Operating pressures between 15 and 25 psi produce large droplets less prone to drift, while maintaining a uniform spray pattern. Although the larger range of rated pressures allows a wider range of spraying speeds, applicators should avoid higher speeds that require pressures in the upper range in order to reduce the production of drift-prone particles. Wide-angle flat fan nozzles are designed with a wider and narrower orifice to achieve the desired 100% overlap pattern at lower boom heights than the more common 80-degree flat fan. The narrower orifice produces a thinner sheet of liquid, resulting in smaller, more drift-prone droplets. However, when operated at the proper height for 100% overlap, the boom will be closer to the canopy and more of the smaller droplets will reach the target. Flooding nozzles create droplets by splashing a stream of liquid through a round orifice onto a plate, producing larger droplets than a flat fan nozzle when operated at low pressures. Flooding nozzles are commonly used for applying liquid fertilizer suspensions because the round orifice is less susceptible to plugging. Flooding nozzles produce a peculiar spray pattern that is difficult to overlap properly for uniform coverage. At higher pressures, a flooding nozzle will produce more drift-prone droplets than a properly operated flat fan. The original flooding nozzle design has been replaced with the turbo flood design, which has both a pre-orifice and a turbulence chamber that reduces liquid velocity, producing larger and more uniform droplets. The improved design also produces a spray pattern that improves uniformity when overlapped properly with adjacent nozzles. The turbo flat fan can also be operated over a wider range of pressures than a single flat fan nozzle. With increased travel speed, select a nozzle with a larger orifice and operate it at lower pressures to produce larger droplets less subject to drift. Avoid operating speeds that require pressures in the upper range. Air induction nozzles produce larger droplets by combining a pre-orifice, which reduces pressure, and a venturi, which draws air into the spray solution much like a carburetor. The air becomes entrained in the spray solution and results in larger droplets composed of water and tiny air bubbles. The air-filled drops are said to splatter as they reach the target, providing better coverage. As noted earlier, the usual forces that determine the course and final destination of a spray droplet are the initial momentum of the droplet, the resistance encountered as it travels through the air, and gravity. There are new technologies designed to improve spray deposition or reduce drift, either by introducing an additional force or providing control of an existing force. Electrostatic sprayers add an electrostatic force to reduce drift and direct droplets toward the plant canopy. While the additional effect of the electrostatic charge is minimal for large droplets, it can be sufficient to guide the smaller, more drift-prone droplets toward the canopy. Air assist sprayers direct a curtain of air into the canopy to increase penetration and deposition of droplets. Their most significant use has been in the application of insecticides and fungicides, where small droplets are essential to provide good coverage and effectiveness. The directed air carries smaller droplets into the canopy, where they are deposited in areas otherwise not accessible by their initial momentum and gravity, such as the underside of leaves and lower foliage that is typically occluded by the top of the canopy. Maximum effectiveness of air assist sprayers is achieved only through proper adjustment of air volume, velocity, and angle, and varies with the type of canopy being sprayed. When properly implemented in crop canopies, air assist sprayers can also reduce drift. Shields change the effects of ambient air speed and direction, which results in better placement of small droplets. The effectiveness of shields in reducing drift depends on a number of factors, including the shape, size, and construction of the shield, the mounting angle and location of the shield relative to the boom, and the droplet distribution in ambient air conditions in which the pesticide is applied. Although properly designed and implemented shields can reduce drift of small droplets, shields should not be considered a substitute for selecting a nozzle that minimizes small droplets. A poorly designed shield has the potential to increase drift in windy conditions, especially when improperly adjusted. Regardless of the type of sprayer and nozzle used for application, it is extremely important that the sprayer be accurately calibrated to assure proper pesticide application. Depending on the type of sprayer, there are various techniques to calculate the amount of pesticide released in a given time. Some sprayers are equipped with computerized calibration for greater precision and convenience. Calibration techniques can be reviewed in the publication Private Pesticide Applicator Training, available from University of Missouri Extension. In addition to nozzle spray angle, spray volume, boom height, and nozzle spacing, the potential for spray drift is also affected by wind speed, wind direction, air stability, relative humidity, and temperature.
When weeds need spraying, for example, they need spraying, and everybody's got to go out there and be spraying them at the same time. If it happens to be a windy couple of weeks, then that's where we can get into trouble, and we've seen some of that in this year in particular. And so we have some off-target movement in those situations.
Air movement largely determines the distribution of spray droplets. Wind is an important factor, but vertical air movement is also a factor. As discussed earlier, temperature inversions provide little vertical movement of the air and allow even a gentle breeze to move spray droplets several miles and possibly result in a severe spray drift incident. Severe drift injury can occur even when wind velocities are low. But as wind speeds increase, the amount of pesticide lost from the target area and the distance it moves increases also. Most recommendations are to refrain from spraying if wind speeds exceed 10 miles per hour. Shielded booms and a lower boom height can minimize the influence of wind.
The greater the wind speed, the more potential for drift that there is. We always want to make sure that we're out applying our products when wind speeds are low and see where, if we do have some drift, where is it going to go? And taking a look at what's on that downward side. Is it a natural area, waterway, watershed? Is it a susceptible crop that can be damaged by the product that we're applying? Is it houses? All those things need to be taken into effect when you're looking at the wind direction.
Pesticides should not be applied when the wind is blowing toward a nearby susceptible crop or a crop in a vulnerable stage of growth. Apply when there is little wind or the wind blows gently away from susceptible crops. If these conditions do not exist, consider either another method of control or another time of application. Also, consider the use of formulations and adjuvants that reduce evaporation. Although pesticides differ in their evaporation rate, as a rule of thumb, relative humidity above 70% is ideal for spraying. Below 50%, special attention to the application is warranted. Some spray adjuvants act as drift retardants or spray thickeners by increasing the number of larger droplets and decreasing the number of finer droplets. Droplets formed by oil carriers are usually smaller, lighter, and evaporate more slowly than droplets formed from a water carrier. Consequently, oil carriers form droplets that remain airborne longer and tend to drift farther.
When we look at our field conditions, we also want to look at what's around our field as far as potential to damage to drift. Looking at what other crops are around. Is it pasture ground? Are there houses, lawns, ornamental plants growing? Is there somebody's garden out there? We want to make sure that we set up buffer zones and not spray right up to those areas so that spray drift has a place to go and to settle down before it gets into those areas.
An important tool in the effort to reduce the potential damage of pesticide spray drift is the Pesticide Sensitive Crop Registry and Locator, also known as DriftWatch. In Missouri and many other states, producers of pesticide-sensitive crops can register the location of these crops online. The location of commercial honeybee hives can also be listed on the registry. When considering the use of pesticides, applicators are encouraged to consult the online Pesticide-Sensitive Crop Registry and Locator in order to be aware of any pesticide-sensitive crops that could be potentially affected by the intended application. Aerial applicators should keep in mind that they are subject to the same spray drift factors, pesticide regulations, and consequences of liability as their ground-based counterparts. However, applicators should also realize that aerial application requires particularly trained personnel and specifically designed equipment and application techniques. In summary, drift can be controlled by maximizing the size of droplets and minimizing the time those droplets are airborne. This can best be accomplished by following these practices. Spray only when conditions are right. Do not spray when wind speeds are as high as 10 miles per hour. Use caution even when winds are light and variable, especially when applications are near susceptible vegetation. Use special caution when relative humidity is below 50% and temperatures are high. Remember, drift is much more likely during the hottest part of the day. Keep the spray boom close to the target by using wide-angle nozzles. Maintain a reasonable application speed, usually between 8 and 12 miles per hour, to avoid operating in the upper pressure range of the nozzle and to minimize bouncing of the boom. Select the proper nozzle design for each type of application. Keep in mind that nozzle replacement is inexpensive compared to the cost of wasted materials, loss of yield, and the potential litigation that can result from a poor application. Calibrate the sprayer and replace worn nozzles. Use higher carrier rates when possible, especially with formulations that are more effective with higher rates. Use drift reduction agents to reduce the number of smaller, drift-prone spray droplets. However, keep in mind that no drift control agent will eliminate drift in high winds. These simple, common-sense procedures are a cost-effective approach to avoiding the potential damage and the liability that can result from pesticide spray drift. These practices can be easily implemented and can not only reduce the potential of spray drift, but can also result in improved pesticide application efficiency and effectiveness. For more information on preventing and reducing the potential for pesticide spray drift, contact these resources.